In Unit 2.4, Part 2, Structure of the Atom, we are going to do three things. Compare and contrast average atomic mass and atomic mass, and do calculations of average atomic mass of an element and percent abundance of isotopes in an element. First, a review. So recall that in the periodic table tiles, you get two numbers. One is a whole number and one is a decimal number. The decimal number is always larger. It shows the average atomic mass of all atoms in an element. The other number, the whole number, is the atomic number, or the number of protons. And you also get the element symbol in the middle. So note that the atomic number is always smaller than the average atomic mass, because the average atomic mass, like the atomic mass of a single element, is the average of all the protons plus all the neutrons of all naturally occurring atoms of that element. So the average atomic mass in the periodic table is roughly equal to the number of protons plus the number of neutrons of the most abundant isotope of that element. Average atomic mass is always larger than the atomic number. So if I ask you, show you this periodic table tile and find the neutrons of a typical copper atom, you're going to just subtract from 63.546, 29, and round it to the nearest whole number, and then you get 35 neutrons. Also recall that atomic mass of a given atom is the mass number of that atom. That is equal to proton number plus neutron number. But the atomic mass of an element is not calculated that way. We looked at this definition in the previous notes. This is the average atomic mass of all the atoms in that element. You can also say it's the sum of the mass times the percent abundance of all isotopes of that in a naturally occurring sample of that element. So you need two things to find the atomic mass of an element: the mass of each isotope, like one atom of each isotope, what's their mass, and then out of all the atoms, isotopes in that sample, what percentage or what abundance is each isotope. So abundance is calculated by dividing the number of atoms of one isotope by the total atoms of all isotopes in that sample. This value, the average atomic mass, is close to the mass of the most abundant isotope, as you will see in the next slide. In the slide after. So quickly, let's compare mass number versus average atomic mass. So if you get a periodic tile for carbon, it's based on the two most abundant isotopes of carbon, which is C12 and C14. So this is the average mass of all of these atoms in a naturally occurring sample, and 6 is the number of protons in all carbon atoms. So if I look at one carbon 12 atom, you could even do carbon 14, but in this example I just use 14. So the mass of this atom is equal to all the protons plus neutrons. Since it has 6 of each, you're going to add 6 plus 6, and the mass is 12. This value is a whole number, but if you look at this carbon element sample with more C12 than C14, your mass is going to be closer to C12 because it's the most abundant one. The weighted average of all the isotopes in this element will be equal to the average So will be equal to the average atomic mass of this element. So that means average carbon atoms in this sample has this mass. So here's an example showing how in these elements and their isotopes in a sample, how you can calculate, how you can estimate the average atomic mass of a sample. So here the most abundant one is hydrogen 1 isotope. It's 99, almost 100%. So the average atomic mass is the same value. For helium, it's helium 4, and so the average atomic mass is close to 4. For carbon, it's carbon 12. It's almost 99%, so the average atomic mass is close to 12. And oxygen, there are 3 isotopes, but the most abundant is oxygen 16. So its mass, average atomic mass of the element sample is going to be close to 16, which is 15.999. Chlorine has 2 isotopes. Most abundant is chlorine 35 with a 76 almost percent. So the average atomic mass of the element is close to 35. So if I ask you to estimate the atomic mass of this element sample, you are going to quickly look at which one is the most abundant. As long as it's not 50-50, this one is 1, 2, 3, 4, 5, 6, right? And 1, 2, 3. So out of 9, 6 of them are C12. So that means this one, the average atomic mass of carbon element in this sample is going to be close to 12. Let's look at doing calculations of atomic mass. So here is the equation you're going to use. The average atomic mass of an element is mass of one isotope. That is the mass of one atom of each isotope times the abundance of that isotope. Say you have 3 isotopes, then you're going to do this 3 times. You're going to have 3 pluses. So mass of isotope 1 times isotope 1 abundance plus mass of isotope 2 times isotope 2 abundance plus mass of isotope 3 times isotope 3 abundance, and you end there. If you have 4 isotopes, you will have another segment with mass of isotope 4 times isotope 4 abundance. You get the picture. So let's do our first question. This is how you calculate atomic mass of an element when I give you the percent abundance. So it's a percentage. Percentage is out of 100 how much. So say element, there's an element called W. It has 2 isotopes. Isotope X10 and isotope X11. So the mass of X10 is 10.012 AMU and its percent abundance is 19.91. Isotope X11 has a mass of 11.009 AMU and a relative abundance of 80.09. Now, if you have only 2 isotopes, when you add these 2 percent abundances, they should equal 100%, and they do. And it's asking you to calculate the atomic mass of this element. So you're going to write your equation. Since you have 2 isotopes, you're only going to do this twice. And you are going to now convert percent abundance to abundance as shown here. So I'm done for the first one, X10. So you're going to convert this into an abundance. So this means 19.91 divided by 100. So when you divide it by 100, you get this value, and that's what you plug in. So you're going to write X10 mass times abundance here's its mass in AMU from over here, times 0.1991 plus X11 mass, which is 11.009, here it is, times its percent abundance. You can directly do this. You're going to move the decimal point 2 places in the front. That's what happens when you divide it by 100. And if your math is bad, just take your calculator and divide this value by 100. Again, you just move the decimal place 2 places. And so that's the value. And then you add the two values you get, and you get 10.810 AMU. If you can check your math, since this guy is the most abundant, it should be close to 11 something, and that indeed it is. 10.8 is close to 11. Second question. How do you calculate the percent abundance? Using the atomic mass. So the question says the atomic mass of copper is this much, and what is which of the two isotopes of copper is more abundant, C64 or Cu65? This is a very simple explanation. Look at this number and see who's close to that number. So 63.5 is closer to 63 than 65, right? So it would be 63. And here's the written explanation. So here's a question where you are shown how many atoms of each isotope are in the sample, and you're supposed to calculate percent abundance. So you are given two isotopes in this sample, and you have to count them, X23 and 22. It says calculate the abundance and the percent abundance of the two isotopes shown. So first thing you're going to do is you're going to draw a table, abundance times percent abundance. You're going to count all the X23s, the black ones. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there are 3 of the other guy, right? So it's 12 out of 15 total atoms, which is 0.8. And that would be 80%. And this one is 3 out of 15, that is 20%. All you do is you multiply this fraction by 100, or this one, you multiply it by 100, you move the decimal 2 places. And then the average atomic mass, since we have two isotopes, you are going to multiply the mass of X23 by its abundance. So 23 times 0.8 plus 22, this one mass times 0.2, and then you get your values and you add them up, and the average atomic mass of this element is close to 22.8. So the last thing we just checked is calculating percent abundance of isotopes of an element. If I give you a picture of the sample, and that's it. I'll see you in the next video.